In this lecture, we will learn about symmetric groups. First, we will review some concepts about permutations. Consider the following proposition. Let f from x to y be a well-defined map. Then the following are equivalent. First, the map F is a monomorphism. We could also say that the map F is injective. This says that if x1 is not equal to x2, then f of x1 is not equal to f of x2. This happens if and only if the map F has a left inverse. This means that there is a function g from y to x such that g composed with f from x to x is the identity map. Next, we'll consider the following proposition. Let f from x to y be a well-defined map. Then the following statements are equivalent. First, the map F is an epimorphism. Second, we could say the map F is surjective. Third, this means that for each little y in capital Y, there exists little x in capital X such that f of little x equals little y. This happens if and only if the map F has a right inverse. This means that there is a function h from y to x such that f composed with h from y to y is the identity map. Note that the order of the composition is different than in the first proposition on the page. Let f from x to y be a well-defined map. Then the following statements are equivalent. The map F is a bimorphism, or the map F is bijective, that is, it is both an injection and a surjection. This is equivalent to saying that the map F has a two-sided inverse. This says that there is a function g from y to x such that both g composed with f from x to x and f composed with g from y to y are the identity maps. We call g the inverse of f and denote it by f to the negative 1, or f inverse. Recall that a permutation of a set X is a bimorphism or bijection sigma from X to X. Then we have the following proposition. Given a set X, let S sub X denote the collection of permutations sigma from X to X. The identity map from X to X, which sends each little x to itself, is a permutation. If sigma and tau from x to x are two permutations, then their composition, sigma composed tau, is also a permutation. Moreover, we have the formula for the inverse of the composition. Sigma composed tau inverse is equal to tau inverse composed with sigma inverse. Okay, now let's consider a set X, and again, the set S sub X to be the collection of permutation sigma from X to X. We can take composition with these permutations, and together this pair S sub X comma composition form a group. For example, if we take our set X to be a finite set of n elements, call them x1, x2, up to xn, then f sub x has n factorial elements. Okay, so if x is a non-empty set, and Sx is again the set of all permutations sigma from x to x, we'll call this pair S sub x with composition the symmetric group on X. In particular, when X is the set of numbers 1, 2, up to n, Its metric group will simply be denoted by S sub n, and this is called the symmetric group of degree n. For example, let's consider the set X to be the set of A, B, and C. This set has size 3. There are 3 elements. So S sub X has size 3 factorial, so it has 6 permutations in the collection. The following diagram shows all 6 possible permutations of the letters A, B, and C. Let's consider going all the way along the left-hand side of this diagram. So this is the identity permutation. This permutation fixes each of the elements A, B, and C. So sigma of A is A, sigma of B is B, and sigma of C is C. For the next permutation, sigma fixes still the element A. So sigma of A is A. Now, however, sigma interchanges B and C. So sigma of B equals C, and sigma of C equals B. For the third permutation, we see that the element C is fixed by this permutation, and the permutation interchanges A and B. So sigma of A is B, sigma of B is A. For the fourth permutation, none of the 3 letters are fixed by the permutation. Sigma maps A to B, sigma maps B to C, sigma maps C to A. In this permutation, B is fixed, and sigma interchanges A and C. And finally, this last permutation is the reverse of the fourth permutation. So again, none of the 3 letters are fixed by this permutation, but this time sigma of A is C, sigma of B is A, and sigma of C is B. Is there a shorthand notation for such permutations from X to X instead of writing out what they do to each element? Okay, so let's return to our example, and we will see an example of what's called cycle notation. So for our set A, B, and C with 3 elements, let's write our 6 permutations out as we did before, now as rows. So this first row is the identity permutation, and then we have the other 5 permutations from before. The cycle notation that we'll write on the right-hand side is as follows. For the identity permutation, each element is fixed. So we'll start with a cycle with the letter A. Since it maps back to itself, we'll close that cycle, and then we'll write a cycle with just the element B and close it, and a cycle with just the element C and close it. In this next permutation, A again is fixed, so as before, it's parentheses, A, and parentheses for that part of cycle notation. Next, we have a cycle where we start with B. Sigma maps B to C, so we write C next to B in the cycle. And then sigma maps C back to B, so we close off the cycle after C. In the third permutation, A and B are swapped and C is fixed. So for the first cycle, we write A, and then sigma maps A to B, so we write B next to A. Sigma maps B back to A, so we close off the cycle. And then we write C, sigma maps C back to C, so we close off the cycle. The fourth permutation will be known as what's called a 3 cycle. And so we'll see the definition of a K cycle in future slides. What happens here is we start the cycle with A, sigma maps A to B. So we write B next to A. Sigma maps B to C, so we write C next to B. Finally, sigma maps C back to A, so we close the cycle. In this fifth permutation, B is fixed, A maps to C, and C maps back to A. Okay, and the cycle notation for this last permutation. This last permutation is the reverse of the fourth permutation. Here, the cycle starts with A maps to C is next to A in the cycle. Then sigma maps C to B, so we write down B in the cycle. Finally, sigma maps B back to A, so we close the cycle. So this is cycle notation. Next, we'll write an algorithm to write cycle notation for any permutation in Sn. So from now on, let's take X to be the set of numbers 1 through n, and let sigma to be a permutation in Sn. The algorithm goes as follows. First, let's pick the smallest integer a between 1 and n, which has not yet appeared in any previous cycle. Let's start the cycle as parentheses a. Second, let's read off b equals sigma of a. If b does not equal a, then write b next to a, i.e. write the cycle parentheses a, b, and continue to the next step. Otherwise, if b is equal to a, we'll close off the cycle, i.e. write parentheses a, end parentheses, and return to step number 1. Next, we'll read off c equals sigma of b. If c is different from a, then write c next to b, i.e. write the cycle parentheses a, b, c, and continue to the next step. Otherwise, close off the cycle, i.e. write parentheses a, b, end parentheses, and return to step number 1. Last, we will continue on in this fashion until we get all of the numbers 1 through n appearing in a cycle. Okay, let's consider an example where we take a permutation in S sub 13. We could write out the permutation by saying what it does to each number 1 through 13. So here's the particular permutation we'll consider. For example, sigma of 1 equals 12. Let's write this in cycle notation. Okay, so first we'll look for the first number, the lowest number that has not yet appeared, which is 1, and we'll write that in our cycle. The algorithm then says we look at what is sigma of 1. That's 12. 12 is different from 1, so we'll write that next to the 1 in the cycle. And next, the algorithm says we look at what is sigma of 12. It's 8, which is different from 1, so we'll write that next to the 12. Sigma of 8 is 10, which is different from 1, so we'll write that next to the 8. Then sigma of 10 is 4, which is different from 1, so we'll write that next to the 10. Now we look at sigma of 4. This is equal to 1, so we will end the cycle and prepare to start the next cycle. Okay, so for the next cycle, we take the smallest number that has not yet appeared in a cycle. In this case, we take 2. Sigma maps 2 to 13. 13 is not equal to 2, so we write it next to the 2. Sigma of 13 is equal to 2, so we close off the cycle and start the next one. The next lowest number that has not yet appeared is 3. Sigma maps 3 to itself, so we close the cycle and start a new one. Now the numbers 1, 2, 3, and 4 have appeared in cycles, so the next lowest number to consider is 5. Sigma of 5 is 11. Sigma of 11 is 7. And sigma of 7 returns back to 5, so we end this cycle. The next lowest number to consider is 6. Sigma of 6 is 9. Sigma of 9 is 6. Okay, we've now completed writing our permutation in cycle notation because all of the numbers 1 through 13 appear in one of the cycles. Notice that this is a much shorter way of conveying the information of where each number gets mapped to by the permutation than writing them all out above. In fact, we can always express any permutation in Sn in cycle notation. So we'll have all of the numbers equal to the set of all the numbers from 1 to n. However, often in these cycle notations, people will not list the 1 cycles since they denote the fixed points of the permutation. And whether they're listed or not, we still know what's happening. Okay, a definition is that the length of a cycle is the number of integers which appear in that cycle. So returning to our permutation in S13, this is the product of a 5 cycle, a 2 cycle, a 1 cycle, a 3 cycle, and a 2 cycle. So it's a 5 cycle because it has 5 numbers in that cycle. Okay, next we can ask, how does cycle notation behave under composition? Since the composition sigma composed with tau is read from right to left, the same is true of cycle notation. Let's do an example. Consider the following 2 permutations in F3. Sigma interchanges 1 and 2, and 3 is fixed by sigma. So notice we did not write down the 1 cycle 3, but it is implied. Tau interchanges the numbers 1 and 3, and it leaves the number 2 fixed. Okay, first let's consider sigma composed with tau. We claim that in the end, this will be the cycle that maps 1 to 3, 3 to 2, and 2 back to 1. So let's consider each element. Sigma composed tau takes 1 first by tau to 3, then sigma maps 3 to 3, so let's say 6. So overall, sigma composed tau maps 1 to 3. Now let's see what the composition does to the element 3. So 3 goes by tau to 1, and 1 goes by sigma to 2. Okay, so overall, this composition maps 3 to 2. Finally, let's look at what sigma composed tau does to 2. So 2 goes by tau, it's fixed, and it goes to 2. Then 2 goes by sigma to 1. Okay, similarly, we can consider the composition tau composed sigma. For example, 1 maps by sigma to 2, 2 maps under tau, it's fixed, so it maps to 2. Okay, so tau composed sigma sends 1 to 2. Now let's see what tau composed sigma does to 2. So 2 goes by sigma to 1, 1 goes by tau to 3. So tau composed sigma maps 2 to 3. Finally, let's see what tau composed sigma does to 3. So 3 maps by sigma, it's fixed, it's mapped to 3. Then 3 maps by tau to 1. So tau composed sigma sends 3 back to 1. Okay, So on the other hand, if we study inverses, these are easier to compute using cycle notation. For example, if we have an M cycle, sigma A1, A2 up to AM, we can write sigma inverse in cycle notation by reversing the numbers in the M cycle. So we'll get AM out to A2, A1. So returning to our permutation from before, we have our cycle, and we can write its inverse by reversing both the order of the cycles themselves and the orders of the numbers in each cycle. So sigma inverse starts with 9, 6, then 7, 11, 5, then 3, then the cycle 13, 2. Then finally we reverse the numbers in the 5 cycle and get 4, 10, 8, 12, 1. Note how the order of the cycles and the order within each cycle is reversed. Thanks for watching.